Okay, so I'm going to continue with the discussion. One thing I noticed, and I'll do a brief recall, one thing I noticed is the first diagram that I drew was not good. I can't draw any better, but I'm going to try to draw it again. So when we talk about the components of a vector, okay, so and my vector A was like this. I didn't draw the lines, the perpendicular lines as well as I should. So you drop a perpendicular, okay? And then if I'm drawing, and so this is my x-axis, if I'm drawing a perpendicular here, it has to be parallel to my y-axis. That, it doesn't look, but this is a perspective drawing, you see? That is a perpendicular. And if I'm drawing a perpendicular to the y-axis, it'll be parallel to the x-axis. Okay? And this one is easier to draw. It is just... And then this is the x component of A. First I project it down to the xy plane, then I drop it down to ax. And this distance over here, or this distance over, same as that, this or this, it belongs here, is AY, and this much is AC. Okay, and you can see how we got the magnitude of A was square root of AX squared plus AY squared plus AZ squared. And you can see how that came about. This length is this length squared plus this length squared, and then you take the square root, Pythagorean theorem. But how do you get this length? Well, you use Pythagorean theorem here. And convince yourself that this is in fact the length of a vector. My notation versus Griffith's notation, this is a vector for me. I think Griffith uses boldface for vectors. I don't easily come in that font. Okay, and the other thing is the magnitude of a vector A. That is just too complicated to write. So it is often written, and when I say equal to, it means it's not a big mathematical result, it's just a definition. Notation is, if you take A and remove the vector symbol, it means it's the magnitude. Okay? And then we talked about the dot product. And this was AX BX plus AY BY plus AZ BC. And we had a geometric interpretation as well. This is, now I can write it as AB times cosine of the angle between them. And I proved this in a nicely chosen coordinate system, but it really doesn't matter. If you have an arbitrary two vectors, A and B, by theta I just mean the length of the, the angle between A and B. In the plane, the unique plane containing A and B. I think this is as far as we went. And we also talked about, I suppose, unit vectors, correct? We talked about unit vectors, x hat, y hat, and z hat. These are vectors of length 1. Well, how do you know what the length of this is? Now you can apply this formula, and in fact, it's trivially 1. And they're also the dot product. So let's do this. I don't know if we did this. What is x dot y? Let's do it the geometric way. Magnitude of this unit vector, 1. Magnitude of this. What's the angle between x and y? 90. Cosine 90. What is cosine of 90? 0. Yeah, so they're all, and all such combinations. So x dot x hat y hat equals x hat dot z hat equals y hat dot z hat equals 0. On the other hand, x hat dot x hat equals y hat dot y hat equals z hat dot z hat equals 1. So they are referred to as an orthogonal triplet. They're unit orthogonal triplets. Okay? And from this definition, it is easy to see that, so from here, A dot B is the same as B dot A. Magnitude of A times magnitude of B is the same as magnitude of B times magnitude of A. Theta is just the angle between them. Yeah? So dot product is commutative. You might say, well, if it is B dot A, do we have to measure the angle clockwise versus counterclockwise? You can. But if you did, there's no problem, because cosine, if you remember, satisfies this relationship. Cosine is said to be an even function, because when you put a negative, it just goes away. Sine, it's kind of odd. Yeah? Okay. If there's a dot product, there's another product. What is that? Cross product. The cross product takes two vectors and returns a vector. There's a geometric formula and there is an algebraic formula. This is what I mean by an algebraic formula and a geometric formula. We'll do both. Let me give the non-intuitive one first. Everyone gives the intuitive one first, but then they don't. If I did that, you would never want to study the non-intuitive one. The non-intuitive one is much more handy in calculation. So if I have vector A and then B, if I take the cross product, well, this is exactly what I'm going to do. I'm going to put a cross in front of it. And then whatever I define on the right side should result in a vector. There's a short way to remember it. If you haven't seen matrices or determinants, not a problem. I'll tell you what it means. If you have, you'll recall what it means. So always, in the beginning, write out x hat, y hat, z hat. Then you take the components of A and then write it out. It is important to write it out this way. A goes here, and then B. Okay? So it's very important that you preserve the rows like I have written. What is the determinant? How many of you have not seen a determinant? It's this times, this times, this times. Yeah? Let me write it out. So it's this guy, and that's what makes it a vector. I'm giving you the x component of the vector. Then you take the determinant of this guy, which is, Travis, you with me? Yeah? And then I go to this guy, but since it's the next one, I put a minus sign. Just remember to do that. This is just a mnemonic to remember what it is. But determinants have a deeper meaning. Now, if I'm doing y hat, I ignore this row and this column. And then I do this times this minus this times this. Now we're back to z hat. So here there's no minus. Here there's minus. Here there's no minus. If we had a fourth dimension, there would be a minus. Okay. Plus z hat. You tell me what goes here.
X, B, Y, A, Y, B.
ax by minus ay bx. This is how you would take the curl, or sorry, the cross product of a vector.
Already?
Curl is coming. It's coming. Yeah, curl lab. You know, vector calculus. It's the 4th course in the calculus sequence. We'll do it in 2 weeks. We'll do much more too. As an instructor, I get to make the problems. So when I do problems on the board, I'm just going to make easy examples. You guys, well, I just make you sweat a little. I won't. Just like to say that. Let's put a number, 2. Let's put a minus sign. Yeah? It doesn't really matter, does it? Because you're just doing, you're just cranking this out. So A cross B equals x hat, y hat, z hat. Travis, tell me what goes in this row?
The ax, ay.
Well, tell me what that is.
That'd just be the components of the A vector.
Yeah, tell me. What are they? I've given you A and B.
Sorry.
Right.
Would just be
What's the x component of A?
just 1.
1.
So 1, 0,
Good.
and then 1.
James, you tell me the next row.
Negative 1, 2, and 0.
Negative 1, 2, and then 0. Yeah? Good. See, it wasn't intentional, but I could just as well put the x hat here instead of there. So you have to, don't make this the x component. It's not the first one. Okay, so let me see if we can do it quickly. This times this is 0 minus 2. So I have minus 2 x hat. Everyone good? I know there's a minus, but I'm going to keep it in my head. And then I have 1 times 0 minus 1 times 1, which is minus 1. No, which is 1. Then there's a minus sign here. This could very well be wrong. If I'm right, I take all credit. If I'm wrong, it's on you. So check. Is that true? I've lost track. You guys are young. You should be able to compute. Yeah? All right. You can look at the textbook and do a few problems, make up your own problems. So this chapter in particular, because it's math skills, we'll have an in-class computational exam. I'll give you a couple of the integral problems for take-home. Okay, that's the algebraic formula. Let's try to get a geometric understanding. So, what will I do? I'll make my life easy, right? For a geometric understanding. I'm going to take the vector A and place it along the x-axis. Yeah. This is my vector A. And then I'm going to take my vector. I don't have a choice anymore, but A and B, I know they form a plane. I just picked it to be the blackboard. I don't have to. And just to end it earlier, I'm going to do B. So now, by this picture, I know that A is AX x hat, and B is BX x hat plus BY y hat. It's on the blackboard, there's no Z component. Amazingly, A cross B will only have a Z component. And we'll see why, because we get a nice result. Okay? Let's do A cross B. Oops. AX 0 0 BX BY BZ. Chip, you want to tell me what the cross product is? Take your time, take your time. Tell me very quickly, the X component, what is it?
0.
What's the Y component?
X, B, Z.
Ooh.
Oh yeah, I was
Yeah.
wondering, I was like,
Yeah.
okay, so 0.
The 0. What's the Z component?
It is AX, BY.
There are a couple of things to be understood from this geometric picture. First of all, A and B is in the XY plane. The cross product is perpendicular to that plane. You may already know this. So A cross B will always be perpendicular to both A and B. I'll give you another geometric picture as well. Now, I can write this differently. I can write this as A cross B. What is AX? Isn't that the magnitude of A?
Yeah.
What is BY? Hold on.
B the direction of y.
Can you tell me BY in terms of the magnitude of B? Martin?
B sine theta.
B sine theta. Almost there. There should be a vector, so I should make this a vector. Okay? It is the direction that is perpendicular to both A and B. So the notation is, well, this is the magnitude. The vector is going to be perpendicular to this, but we already took care of the magnitude, so it better be a unit vector. So the notation is N for normal and hat for unit vector. But there's a little bit of, there's a conversation to be had here, because now sine theta could be plus or minus. Yeah, so let me explain. Unit normal to the plane, unit normal to vectors A and B using the right-hand rule. We'll use the term right-hand rule all the time. Might as well come up with an acronym. So what is a right-hand rule? Here's a problem. I have two vectors. Let's say, it doesn't matter, one vector here, one vector here, in this plane. So I know if I want to pick a unit normal to A and B, I really have to be careful. I can pick this or I can pick that. Which one do I pick? It is given by the right-hand rule. So let's make it this way. This is my vector A, B is at some angle. Okay? Take your right hand. Take the edge of your palm place it along vector A. Sweep towards the vector B, and your thumb points in the direction of the right-hand rule. So in this case, again, it's a 3D drawing. This is going to be like, if it's like this, you know what I'm trying to say? I'm trying to draw a perspective plane as opposed to, yeah.
Where did the unit thing come? Why did we need that?
Oh, yeah, right. So this is the magnitude. So this is this, right? In this problem, it is a unit vector perpendicular to A and B, but it just so happened to be z-axis. In general, it doesn't have to be z-axis. Yeah? It could be just any axis. So, but we've already taken care of the magnitude. So whatever this direction is, we don't want it to have any magnitude, or rather, we want it to have unit magnitude, because the magnitude has been taken care of.
Okay, yeah.
We don't want to change the length of the vector anymore. Okay, so if I have two vectors A and B, I take the magnitude of A, I take the magnitude of B. Now, I use my right hand and sweep from A to B. Oh, I should say this as well. Sweep from A to B through the smallest angle, because you guys will catch your nose the other way around. I don't want you to do this. Use the smallest angle and then extend your thumb. That's the. Why should the universe have a preference? You know what? Let's pick the same vectors, because it really doesn't change much for us. And we'll try a couple of things for intuition. And this time around, let me do it so that I don't make a mistake. I'm going to put minus x first and 2 y hat. And then I'm going to do a, did we do an example already? Oh, we did, right? We did. Then I want to do something else. Because now you know how to take it. Just to see how the coordinate unit vectors are. Ashik, components of x hat.
Are we doing the same one?
No, we're doing x hat cross y hat. So this is my first vector. That's my second vector.
1, 0, 0.
1, 0, 0. What about y hat?
0, 0. I mean 0, 1, 0.
0, 1, 0. Look, stare, and tell me that this is true. This is the only one that will contribute. This times this. Yeah? So if I take x hat cross y hat, I know this from my geometric formula. It is z hat. Now, you can similarly show if I do a cyclic permutation, keeping the order, and if you want, I'll let you check this. I get x hat. You know what do I mean by cyclic permutation? I have x hat, y hat, z hat. So I do it, if I do this cross this, I get this. Then if I do this cross this, I get that. Yeah? And then if I do z cross x, I get y. It's easy to do. You don't have to necessarily do this crank. Look at this, z cross x is that y. I'm just saying z hat cross x hat is y hat. You should be able to see it both formulaically, geometrically, and just using your right hand. But when in doubt, you just put it into either of the two formulas. This versus, well, the determinant formula. Okay? Let me do this. I'm going to break the order. I'm going to go backwards. Can you tell me what that is? Use the right hand. Negative. So it's this versus that. If you write out the formula for A cross B using determinants, and then if you write out the formula for B cross A using determinants, what will you find? An important property that this is called a cross product or sometimes a vector product. They do not commute. In fact, they anti-commute. 3 times 2 is 2 times 3. But A cross B is minus B cross A. It's unusual. It's a new algebra where you take the operation, which is a cross product, and you take two of the objects, and then you apply the operation, you'll get a negative number. So this is an important feature. Now with these guys, you know the dot product, you know the cross product. You can create all sorts of identities which can be verified just by writing out the formula. And I don't recommend you memorize it. In the homework, I've assigned 1 or 2, but more importantly, let me show you where to find them. The important ones are, again, the genius features of the book. It's in the front cover. It just becomes very handy. So let's look at some of them to see what are we talking about. This is called the triple product. So yeah, you first take the cross product of B and C, and then you take that vector and you dot it with A. There's a triple product formula, which means, again, you can do a cyclic permutation. Means start with B, and then go to C, and then go to A. What do I mean by that? B, and then you put dot product, C cross. You can do it one more time. C dot A cross B. Is it worth remembering this? No, not at all. If I put you to task and in the exam ask you to show this, can you show this? Yeah. First you take B cross C and you write it out. And then you do a dot product with it. So it has meaning. The more you work with it, the more the meaning will sink in. But let the meaning sink in through physics rather than uninsightful calculation. This is called a triple product. This is the triple dot product, I suppose. There's a triple vector product, which has a nice formula. And I'm doing it now at the moment, only because it has a name that you can remember it by. It's called back cab. And it is B for back and A dot C minus cab C A dot B. So this is a vector, so that better be a vector. That's fine, because A dot C is a number, or it's a function or whatever it is, times a vector, which is a vector. Same thing, this is a function or number times a vector. If I subtract 2 vectors, I get a vector. Okay, so there are things of that nature. Yeah. But Let me just do it here. I think the easier path would be to leave the camera stationary and just use 1/2 of the board, unless we need like the whole board to do a long problem. We have to do calculus at some point.
Is that triple product also called the box product? Is that a different thing?
Box?
Yeah.
No, that's different.
it?
That's the Laplacian.
Oh.
In fact, that's the 4-dimensional
I don't
Laplacian.
know where I got it from, but
Yeah.
I remember it.
Yeah. So things like this.
Yeah.
Yeah. We may see this, but you know this from relativity.
Probably,
It's
I
just
remember
this.
it's just a-
That's what it is. Okay, so let's do calculus. Suppose I have a function. Again, I'll draw x, y, but I don't want to draw x, y. There could be x, y, and z in here, okay? But I'm going to go from one point in space to another point in space. This is my initial point, and this is my final point. And maybe I'm studying the temperature of the surface or three-dimensional area. It may not be temperature, it could be the magnitude of the electric field. It doesn't matter. I'm just studying some value, some function that depends on x, y, and z. So because I have final, I won't pick f as my function. I'll pick a function t. T is a function of the variables x, y, and z. What I would like to know is as I go through the curve, as I go through a path, how does the value of t change? Okay? Now, how do I describe a curve? I can write this curve as a function of s, some s, so that this is the point x of 0 where I'm starting, and I can make this s of anything I really want. Now you might say, oh, s of 1. That's a curve. What do I mean by that? So if I write x of s, then I have the coordinate, the x coordinate is some function of s in the x hat direction, y coordinate as some function of x, s in the y hat direction, and z, which is a function. Is that altogether confusing? Can you give me an example of a curve? Well, that's easy to do. What curve is that?
Is that an S hat?
Who?
X hat.
What curve is that? Recall the equation of a parabola? So instead of x, I just call it s. Then y is x squared or s squared. This is the point x of 0, because it's 0, 0. That's the point 1, 1. This is the point -1, 1. Because I can pick s to be negative, when I do s squared, I'm going to get 1. This curve can go more. I don't really care. And I don't really even require this to be x of 1. It could be just anything. I don't even want to necessarily make this s of 0. I can start my... Very often, if we're doing physics, this s will be replaced with time, t. Something will be a function of time. It's moving. Right? Now, the point is, I'm not interested in this path. Well, I am, only because I want to know what the temperature is along that path. Yeah? So there are many ways I can think of this function. I can think of temperature being a function of s. But it's really not directly a function of s. Temperature is a function of position. It just happens that along the curve, the position is a function of
S.
s.
Yeah.
So if I want to know, as I go along the curve, how does the temperature change, or what is the rate of change of temperature, I could do, for example, dt ds. You may recognize this as chain rule, or almost there. Using, how many of you have taken calculus? If you haven't taken it, it's not a big deal.
Calculus.
3. Can you tell me? Travis, I know you haven't taken calculus. Yeah, it's not required. So let me tell you the result, and then tell me if that makes sense to you. Okay? T varies as x varies. So what do? I take derivative with respect to x first. I can forget the other ones. Hold on 1 second. But then x also varies along along s. So now, what's the difference between this derivative and that derivative? Hold that thought. Again, what's good for the goose is and Travis is going, well, that's not fair. This is not part of the prerequisite. What's with the squiggly derivative? Partial derivatives are just as easy as regular derivatives. If you have functions of several variables, when you take, this is called a partial derivative. You treat as if all the other variables are constant. Let me give you an example. Suppose I have a function, f of x, y. Give me a good function. Just to distinguish one from the other. Yeah? If I take the partial with respect to x, I write first of all like this. It's a partial derivative, not a total derivative. You take the derivative of x squared, but you pretend as if y is not a variable. So, Travis, you tell me, what's the derivative of x squared? 2x. And pretend y is like 2. What is this? Good. That's it. And this is called the chain rule. Now, t is a function of x, y, and z. And so, I can only take partial derivative. But along the curve, x is only a function of s. So it's my normal derivative that I know of. This is called chain rule. It's a result in math.